Hello everybody, and welcome to our last unit of new material, differential equations. So let's go ahead and start off by talking about what a differential equation is. Okay, so up until now you have looked at a lot of different equations. There are some examples on the screen. The solutions to all these equations have been a number. So if I am trying to solve the equation 10 equals 2x plus 5, the solution to this is 5 halves. And you do that by solving, you get a number. So the solution to this is a number. 5 halves is a number. In differential equations, so here's an example of one. It is an equation about equations. So the solution to a differential equation will be an equation. So here's an example of a differential equation. Y double prime minus y equals 0. So the solution to this differential equation is some function y that when I take the second derivative and then subtract that equation, I get 0. So it's important to keep in mind here that the y in this differential equation stands for a function. And we are trying to figure out what that function is, the solution function, that fits this criteria. So the first thing we're going to do here is check to see if maybe the function y equals sine x is a solution to this differential equation. So anytime we are checking to see if a function we have is a solution to a differential equation, we're going to start off with this setup. We're going to write out what the differential equation is that we think we might be solving. So that was given in the problem. We were also told a potential solution, so I'm going to write that. And then we're going to look at the differential equation. A differential equation will always involve derivatives. It could be the first derivative or second derivative of y. It might be both. A differential equation will always involve y, y prime, y double prime. So I'm going to look at the differential equation and see which derivatives I need to find in this equation. I've got a y double prime. So before I can check to see if sine of x is a solution to this equation, I need to find y double prime. So I'm going to start with, so you're always going to be taking derivatives of the potential solution. So the first step, take any of the derivatives you need that appear in the differential equation, take those derivatives of the potential solution. So all right, so the derivative of sine x is cosine x, so y prime is equal to cosine x, y double prime, so take the derivative of y prime. The derivative of cosine is negative sine x. Okay, so now I'm looking at the differential equation to plug in and check to see if this is a solution. I need to know y double prime. Check, I know that. I know y because that was given in the problem. So now I have enough information to plug back in. To the differential equation and verify. Okay, so I'm just going to plug in y double prime is negative sine x. And then I'm going to subtract y. Y is just sine x. Is that equal to 0? And the answer is no, because I get negative 2 sine x. And that is not equal to 0. So y equals sine x is not a solution to the differential equation y double prime minus y equals 0. So one thing to notice here is that while it is true that for some values of x, negative 2 sine x equals 0, in order for this to be a solution, when I plug this in and verify, I need to get 0 equals 0. It can't be something that's sometimes true. It has to be always true. This little equation here, negative 2 sine x equals 0, that is only true for some values of x. If the function we're looking at is actually a solution to the differential equation, you will get something that's always true, not just for some values of x, but for all values of x. Okay, so now we have discovered that y equals sine x is not a solution to this differential equation. Let's try verifying another one. So here we're going to check to see if y equals 4e to the negative x is a solution to the same differential equation, y double prime minus y equals 0. Okay, so I still need the same derivatives as I did before. I need the second derivative. So I'm going to start off with y equals 4e to the negative x. Y prime is going to be negative 4e to the negative x. Because remember, for an exponential function, it's the original function times the derivative of what's in the exponent. Here, the derivative of the exponent is just negative 1. Okay, so y double prime, I'm going to flip back and get positive 4e to the negative x. All right. So now I can plug in and verify. Okay, so y double prime was 4e to the negative x. Y was given in the problem, it's 4e to the negative x. We're checking to see if that's equal to 0. And in this case, we see we do get 0 equals 0. This is a solution. So the function y equals 4e to the negative x is a function where if I take the second derivative and subtract the original function, I will always get 0. Another way to think about this differential equation is that these are functions where the original function and its second derivative are equal. That is when you verify a solution. This is what it will look like if a function is actually a solution to a given differential equation. So I think some of the key takeaways here are when you are verifying, keep track of which part of the problem you're given is the actual differential equation and which is the potential solution. You're going to use the differential equation to see which derivatives you need to compute, and then you will take those derivatives of the potential solution. One of the most common errors is that people will start trying to differentiate the differential equation, and that's not going to get you anywhere. You always should be taking derivatives of potential solutions. Okay, I think we've covered that. Gone too far. Okay. So we just checked to see that y equals 4e to the negative x was a solution to this differential equation. Y double prime minus y equals 0. Here are a couple more solutions to try to check to see if they are potential solutions to see if they actually work for this differential equation. So why don't you go ahead and take a second and see if y equals 3 times e to the x is a solution to this differential equation, and y equals negative 10 e to the x. I'll go ahead and pause it. You can see what you think. Okay, so here I check both of these. For 3e to the x, y double prime is 3e to the x. So when you subtract y and y double prime, you get 0. And same deal for y equals negative 10 e to the x. Y double prime is also negative 10 e to the x, so when you subtract them, you also get 0. So both of these are also solutions to the differential equation y double prime minus y equals 0. So you might have guessed that, in fact, we can put any coefficient in front of e to the x. And so a lot of times we'll say the general solution to the differential equation y double prime minus y equals 0 is of the form y equals c times e to the x, where c can stand for any constant. No matter what that constant is out in front, the second derivative will always be the same as the original function, so it will satisfy the differential equation. So the general solution will often have a c in it to represent that it can be any given constant. So the solutions that we've been looking at so far things like y equals 3 e to the x, y equals negative 10 e to the x, where there's an actual number filled in for c, those are called particular solutions. So a lot of times what we're going to be doing is solving for a general solution and then using some extra information that's given in the problem. It might be initial conditions. It might be, the solution equation goes through a certain point, and we will use that in addition to the general solution to find a particular solution. Okay, so let's look at an example of that. Okay, so here we are given, we want to verify that this potential solution is a solution to the differential equation 3x plus 2y times y prime equals 0. Okay, so let's just handle that part first. So I want you to identify which one of these is the differential equation, which one of these is, what part of the given problem is the potential solution. So go ahead and pick those out. I'm going to fill them in. Okay, so in this example, the differential equation is the one in green, 3x plus 2y times y prime equals 0. And the potential solution is 3x squared plus 2y squared equals c. Okay, and we need to find y prime, because y prime appears right here in the differential equation. And then we'll go from there. In order to find y prime, you are going to need to differentiate the potential solution. Because of the form of this potential solution, you're going to need to use implicit differentiation. So go ahead and see if you remember how to differentiate this equation implicitly, and then solve it for dy dx. So remember, y prime and dy dx mean the same thing. So why don't you go ahead and give it a swing. Okay, when I differentiated implicitly, I got 6x. Remember, terms that just have an x in them, you treat them normally. And then when I took the derivative of 2y squared, I got 4y times dy dx equals 0. So this c, this constant, whatever it is, when we take the derivative, is going to go to 0. And then down here on the bottom line, I'm just solving for dy dx. And eventually I get to negative 3x over 2y. That is what y prime is. So what I'm going to do now that I have y prime is I'm going to plug that back into the differential equation and see if it actually works, if I get a true statement. So now that I've taken the derivative of a potential solution, I'm going to plug back into the differential equation and solve. So you go ahead and try that as well. And I'll put this up on the screen. Okay, so when we plug in negative 3x over 2y for y prime, we get 3x plus 2y times negative 3x over 2y. Is that equal to 0? The two y's cancel. We have 2y and then a 2y in the denominator, so they cancel. You just get 3x minus 3x, and that is in fact equal to 0. So the conclusion is that our potential solution here, 3x squared plus 2y squared equals c, is in fact a general solution to the differential equation we were given. So then part B asked us to find a particular solution so that our equation for the general solution goes through the point 1, 3. So all you're going to do here is plug in 1 for x and 3 for y and solve for c. So this is similar to like the particle motion problems where you were given initial velocity or initial position and you just plug that information in to solve for c. Same deal here. So I'm going to get 3 times 1 squared plus 2 times 3 squared equals c. You get 3 plus 18 equals c. C equals 21. So the particular solution is 3x squared plus 2y squared equals 21. And that's all there is to it. Okay. Now these are the solutions we just went through. Yep. Yep, C is 21. Okay, so here's an example for you to try. We're running low on time, so I'm going to pause this and let you tackle it. So here's a potential solution and a differential equation. Okay, there's a lot on the screen here, but on the left half, this is where I'm taking a derivative. In order to take the derivative of y, you need to use the product rule on this first term because it's x squared times e to the x. You get this for y prime. Then you need to plug into the differential equation x times y prime minus 2 times y.